Hello everyone. Welcome back to this lecture series on design of RCC structures. So far, we have discussed the working stress method, its assumptions and limitations. Analysis has been carried out for under-reinforced and over-reinforced section, which are then concluded with the design of singly reinforced and doubly reinforced beam examples. However, in modern RCC design, we mainly follow the limit state method, which is recommended by this IS 456-2000. So in today's lecture, we'll focus on the basic concepts of limit state method, the assumptions which are used in the flexural design, force equilibrium in RCC sections, and finally the moment of resistance and limiting moment of resistance. So this lecture is very important because all RCC design using IS codes is based on these concepts. So the limit state method is a design philosophy in which a structure is designed to satisfy two main limit states. They are limit state of collapse as well as the second one is the limit state of serviceability. So this lecture we will concentrate on the limit state of collapse under flexure, which governs the strength design of RCC beams. So the aim is to ensure safety against failure while also achieving economy and ductility. So before deriving any equations, IS 456 makes certain assumptions regarding material behavior. So the most important assumptions are the plane sections before bending remain plane after bending. The maximum compressive strain in the concrete at the extreme fiber is 0.0035 in bending. The tensile strength of the concrete is ignored and the steel follows an elastic plastic behavior, whereas the maximum strain in the tension reinforcement in the section at failure shall not be less than Fy divided by 1.15 ES plus 0.002, where Fi is the characteristic strength of the steel as ES is the modulus of elasticity of steel. In limit state method, we do not assume linear stress distribution up to failure like we followed in the working stress method. So instead, we consider the actual strain behavior of concrete as well as steel at ultimate load. So these three figures being derived from IS 456-2000, in which figure 21 shows the stress strain relationship of concrete in compression and how it is modified in limit state method using the partial safety factor for concrete. So what the actual behavior of concrete is? The concrete exhibits a non-linear stress strain relationship. The stress increases with the strain up to a maximum. Beyond a certain strain, the concrete crushes suddenly, in which the concrete failure is considered as a brittle without giving any warning. So as per IS 456, characteristic compressive strength of the concrete is denoted as FCK. So the concrete strength in a real structure is less than the cube strength because of plenty of effects. One such effect is the size effect, the shape of the specimen, the casting and the compaction differences may be having, curing conditions, even though micro cracking may be taking place in the members. So this reduces the concrete strength by nearly 1/3, and hence the structural strength will be taken as 0.67 FCK only rather than going with the FCK. And this will be further reduced to 0.45 FCK by dividing this 0.67 FCK by the partial safety factor of 1.5 which has been assumed for concrete. So this lambda m represents the partial safety factor for material. In this case, we are considering for concrete, so that it will be taken as 0.67 FCK divided by 1.5, which comes as 0.45 FCK. So this reduction ensures safety against the material variability as well as conservative design at a ultimate limit state. Now moving on with the figure number 22, wherein the stress block parameter has been shown only above the neutral axis. So this figure 22 shows the idealized rectangular parabolic stress block used for concrete in compression as recommended by this IS 456-2000. So we have a combination of a rectangle as well as parabolic shape. Unlike what we had it in the case of working stress method, we had a rectangular or a linear variation. So from figure 22, the resultant compressive force in concrete can be given by 0.36 FCK into B into XU. Right. So why this 0.36 appears in this formula means the maximum design stress in concrete is 0.45 FCK. That's what we derived now. So average stress over the compression zone will be taken as 0.36 FCK. So this accounts for the parabolic stress distribution as well as the partial safety factor, which is nothing like how we are getting this one is 0.45 FCK. This is 0.45 FCK into 0.8. So that's what you'll be getting it as 0.36 FCK. So the resultant compressive force does not act at the extreme fiber. So it acts at the centroid of the stress block. So from the stress block geometry, the distance of CU, this is what is the CU, the total compressive force. The distance of CU from the top has been assumed as 0.42 XU based on the calculations of a combined rectangular as well as a parabolic shape. So this value comes from integration of the stress block, the centroid location of the equivalent stress distribution, and here the 0.36 gives the magnitude of the compressive force, and 0.42 XU gives the location of that force where it has been given. So both are essential for calculating the moment of resistance. Now moving on to figure number 23, which represents the stress strain curves for the reinforcement. So steel initially follows the Hooke's law, wherein the stress is directly proportional to strain. So it yields at yield stress Fy. It yields at yield stress of Fy. So after yielding, the steel undergoes large strains without much increase in the stress. So this provides ductility and warning before failure. And we know that the partial safety factor for the steel is 1.15. Therefore, multiplying this characteristic strength with 1.15 partial safety factor, we will be getting the design strength for the steel as 0.87 Fy. This is what you will be using in the designs. Now let us look at the section details used in the flexural analysis. Since we are considering a singly reinforced section, the area of the steel is being provided only in the tension zone. And already we assumed B is the width of the section, small d represents the effective depth of the section, capital D represents the overall depth of the section, in which Cu represents the total compressive force in concrete, Tu represents the total tensile force in steel, and Z represents the lever arm, that is the distance between the total compressive force and the total tensile force. Whereas AST represents the area of the steel provided in the tension zone. So here under bending, the concrete resists compression and the steel resists tension. So these two forces together, forms a couple. So it will form a couple like this. Forms a couple which resists the applied bending moment. So here the neutral axis is available here. The depth of neutral axis is being considered as XU. The remaining distance is D minus XU. And this is the strain diagram wherein the maximum tensile strain is being considered as a epsilon ST and the maximum compressive strain has been taken as epsilon CO. As per the assumption, this value has been taken as 0.0035. And the total compressive force, as per the assumption, it is acting at a distance of 0.42 XU. Therefore, the lever arm is Z is equal to D minus 0.42 XU. And the total tensile forces, the tensile stress is 0.87 Fy. So after dividing the characteristic strength with the partial safety factor of the steel of 1.15, you will be getting this one 0.87 Fy. Now let us consider how this neutral axis depth can be measured. So at the ultimate limit state, concrete above the neutral axis will be in compression and the concrete below the neutral axis is cracked and hence it will be ignored. So as per IS 456, we will be having Cu will be equal to 0.36 FCK B into XU, and then Tu will be equal to, that is the total tensile force in the steel is 0.87 Fi AST. So once if you are applying the force equilibrium, that is Cu will be equal to Tu, you will be getting 0.36 FCK BXU, which is equal to 0.87 Fi AST. On simplifying, you can able to get the depth of neutral axis. So XU will be equal to 0.87 Fi AST divided by 0.36 FCK B. So this is what has been given in annexure G 1.1 A of your IS 456 2000. So it has been given in the code as XU by D, which will be equal to 0.87 Fy AST divided by 0.36 FCK BD. This is what has been given in the IS code. So here D and D will be getting cancelled. That is what we derived. XU is equal to 0.87 Fy AST divided by 0.36 FCK B. Whereas this formula is valid only your neutral axis lies within the at the actual depth of neutral axis lies within the limiting value, that is XU is less than or equal to XU max. So from this equation we can determine the actual depth of neutral axis XU. So in addition to the force equilibrium, the strain compatibility also must be satisfied. So that is what from the strain diagram, so XU by D will be equal to 0.0035, that is the maximum compressive strain, divided by 0.0035 plus epsilon St. And also you can see from the strain diagram, the strain in steel depends on the position of the neutral axis, and the equations whatever we derived is applicable only when XU is less than or equal to XU max. Here XU max is the maximum permissible depth of neutral axis. It purely depends on the grade of steel. That is what has been given, which has been taken from your IS 456. So for different grade of steel, we have a different XU max by D. So this condition ensures that the steel yields before concrete crushes, providing a ductile behavior. So based on the value of XU, RCC sections are classified as under reinforced section when XU is less than XU max. So here in this case, the steel will yield first, which results in a ductile failure, which are mostly preferred in design. On the other hand, when XU is greater than XU max, it shall be treated as over reinforced section in which the concrete crushes before steel yields, wherein we can experience a brittle failure which is not permitted in practice. And the final case is the balanced section in which XU is equal to XU max, in which steel yielding and the concrete crushing occur simultaneously, which represents the limiting conditions. Now let us define the moment of resistance. We know the definition for moment of resistance. This is the maximum bending moment a section can take care without causing any failure in the section. So here the total compressive force Cu and the total tensile force Tu act at a distance Z apart, so forming a couple that we have already discussed. So hence the moment of resistance Mr can be given as either Tu into Z or Cu into Z, depending on the type of section. So here the lever arm is Z is D minus 0.42 XU. So substituting the expression for forces for under reinforced section, will have Tu into Z, that is 0.87 Fi AST into Z is D minus 0.42 XU. So alternatively, this can also be written as Mr will be equal to 0.36 FCK BXU into D minus 0.42 XU if I am applying the condition Cu into Z. So this equation, the first equation, whatever we derived, will be applicable only when XU is less than or equal to XU max. Whereas the second condition is applicable for all values of XU. So this is what has been given in the IS 456 Annex G 1.1b as well as C in a different form, expanded form, 0.87 FIAST up to this one has been given, in which D minus 0.42 XU. Here the XU formula has been derived in the previous slide of 0.87 FIAST divided by 0.36 FCKB. So substituting that value, the extended form of that equation of the moment of resistance has been given in IS 456. Similarly, the limiting value is also been given in this way. So these equations are the fundamental and are used repeatedly in RCC beam design. Now let us move with the limiting moment of resistance. So when the section is said to be balanced, that is XU is equal to XU max, the corresponding moment of resistance is called the moment of or the limiting moment of resistance. So as per this IS 456-2000, the limited moment of resistance depends mainly on the grade of steel, grade of concrete as well as the ratio XU max by D. So this value represents the maximum moment capacity of a singly reinforced section. And this MU limit has been given under this G 1.1C of IS 456 and extended formula. So once if you know the grade of steel and based on the grade of steel, the XU max by D is available in the IS 456. Substituting that values, we may be getting the reduced formulas for calculating the moment of resistance for different grade of steel. So for instance, if you are using the mild steel reinforcement, that is Fe250, the MU limit will be 0.149 FCK BD square. On the other hand, if you are using the HYSD bars of Fe415 grade steel, in the sense, MU limit will be calculated as 0.138 FCK BD square. So to summarize today's lecture, limit state method ensures safety and ductility. Flexural design is based on force equilibrium and strain compatibility. The neutral axis depth determines the behavior of the section, and the sections are classified as three things: under reinforced, over reinforced as well as balanced. And finally, the moment of resistance has been obtained from the internal force couples. So in the next lecture, we will apply these concepts to the design of a singly reinforced RCC beams using limit state method as well as assumptions. Thank you.